Today we are going to be covering Broadband 101 or Broadband Technology Basics. And really it's to provide what I would call a 30,000 foot view on how all of this stuff works. So I want to take you on that ride, a 30,000 foot view ride. And, much like on an airplane, sometimes there may be some bumps and turbulence, but please don't hesitate to put a question in the chat box that we can get to. And I ask that you, buckle up and come along with me. There we go. So the goal today is to really to demystify the internet technologies and broadband issues more generally. And much like you see here in this slide with the faucet and the electric transmission lines and heating, etc. The point of this is that you don't need to know the difference between passive optical networks and GPON and XGS-PON and all of these technical things to really engage on these issues, just as we don't need to be electrical engineers or water plant managers to engage on how important these utilities are for our lives. And so this whole presentation is really geared towards, again, demystifying some of the technology and issues surrounding it so that hopefully as we fly over the digital landscape, you'll leave with more confidence and a more general understanding of the various issues and particularly the technologies that are at play. Now, the term broadband gets thrown around quite a bit, and I'm old enough to remember before the internet, of course. I'm actually old enough to remember when TV went off the air at a certain time. But I think many of us on this Zoom call do remember the dial-up days where you would unplug your phone, you'd plug it into your computer, you'd hear that funny, iconic sound that I won't try to imitate. And that is how we connected to the internet in the early days, in the mid 90s. Of course, that's not broadband. Broadband is, to oversimplify, is always on internet access, or I should say always on high-speed internet access. And on this slide here, there's a scan code here, but it also gives a little screenshot of these fact sheets that we put together in partnership with the National Digital Inclusion Alliance and AARP that they're not heavy on graphics, they're more heavy on words, but they really do, I think they really do a good job explaining the basics of broadband and what some of the challenges are that communities are facing across the nation. Now, when we think of broadband, I think it's important to begin with how we think about the needs that we all have. And it's more important to think of broadband in terms of household needs, not so much individual needs. And so it's interesting. Sometimes when I go and talk to folks, I ask in the audience, for folks to raise their hand if they know how many devices in their home are connected to the internet. A few hands shoot up. Folks aren't really sure. Even the ones that are pretty confident that they know end up revising their list because they end up forgetting about a number of devices in their home that are connected to the internet. And so the way to think about the needs that we have are in terms of household units and not individuals. And it's also important to keep in mind that in this modern age, where many of us have children who are going to school online, or we're working from home, or we're thinking about telehealth, or we're thinking about things like Nest security cameras, smart TVs, smart thermostats, all of these devices that are connected to the internet more and more, and this is exponentially grown over the years, have a need for upload capacities, not just download capacity, meaning that we're not just consumers. We're not just going online to buy stuff or to see what folks are talking about on social media. Not to say that those things aren't part of life, and entertainment, and these things are important, but we're not just consumers. We are also participants and producers who need to send information upstream, meaning we need to upload information from our computers. For example, me being on this Zoom call, and this video, the video information needs to be uploaded. So upload capacity has become increasingly important, and we'll talk about that a little bit more. The point here, I think, to remember is that we need networks that can handle peak traffic conditions, both in terms of our download needs and our upload needs. And I often draw an analogy with roads or bridges, and I'll refer to that, throughout this presentation. But when you think about the way roads and bridges are built, ideally they're built to handle peak traffic conditions. Now, it doesn't mean that there's no traffic on roads, of course, but still, in terms of the engineering and construction, they're built with a mindset of when there's peak traffic on the roads and the bridges need to be able to handle that. And much like, and that's the same way to think about broadband, or like electricity. When you are in your home and you're turning on a light, we don't think about it in terms of, well, we need to make sure we've got enough to power the refrigerator and click on the kitchen light, or to turn on the TV. We have it set up where anytime you need any electrical device to work in your home, you flip a switch and it works and it turns on, and you have electricity as long as the power is on. And so it's a similar way in thinking about broadband needs and building networks to support that kind of level of connectivity. Now, in this broadband realm, I should say, hear the word broadband access. That word access kind of tossed around quite a bit. And actually, when you think about it, that word access does quite a bit and can be a little bit confusing. And so one distinction I think that is important that we think about is the difference between availability or access. So broadband availability, which is, I think, the primary focus in Appalachia region throughout the numerous states, is about the physical infrastructure, the poles, the conduit, the wires, the electronics. That's what we mean when we talk about broadband availability. Now, access, which is sort of a broader term and does include whether or not broadband is available, the physical network is available, but access is much more about, is it okay, the service or the infrastructure may be available, but is the service affordable? Is it reliable? It involves things like, do you have the right devices to access these things? Do you have the right digital skills to access these things? All of those things fall under the term access. So that's one distinction we should make here. Now, this slide here is something that sometimes confounds folks, because a lot of people think the digital divide is sort of between rural America and urban America, which is an oversimplification. And it's about sort of the confusion between availability and access. Because as it turns out, even though there are more homes in urban areas that do not have access to high-speed internet cumulatively, the sheer numbers, than those who live in rural areas. However, in rural areas, the lack of internet access is much more about availability, whether or not the physical infrastructure is in place. Which is why it's such good news, before I move to the next slide, which is why I think this is such an important moment with this historic, as many folks refer to it, and it's true, this once-in-a-generation investment from the federal government in broadband infrastructure. And BEAD was designed to funnel most of that money to rural communities that lack the physical networks. But let's just pull back just for a second, because I want to take you on a little tour, just so you have again, sort of a 30,000 level understanding of how all this stuff works. How does the the internet work in its most simple and basic form. So this slide here is really to show that how kind of the sort of the computer science behind it. And so you see on the left hand side and also on the right hand side the human readable data. So the device that you're looking at me on and listening to me on, your device is converting all of the ones and zeros that make up the bits of information that are my face, my voice, this Zoom connection, the things that you see on the World Wide Web, et cetera, et cetera. All of that has to be, all of those ones and zeros have to be translated into something that we can read as human beings, or read and visually understand and hear. And so that's what our devices are doing. And so my image, my voice is being converted into these bits of ones and zeros. And then my device is sending out those ones and zeros through a physical signal, be it a radio wave or a light wave. And that information is transported along these networks, the infrastructure that needs to be in place in order for us to have these kind of conversations and connections and access to the internet. And that information, of course, travels over a network, and that signal is received. The bits are translated into human readable format on your devices, and almost seemingly like magic, voila, we've got a Zoom connection. And so when we think about what is a network in its simplest form is simply computers or devices talking to each other. And they can be small, as small as 2 computers. That actually can be a network, or devices, computer and devices talking with any number of computer and devices that are transmitting information to each other. And so then we get to the foundation of the word internet itself, which comes from inter-network. So essentially, the internet is a network of networks that connects local networks to each other and also to the global internet. It's a marvelous bit of technology that was created in the late 60s and has evolved to the point where it was able, it began as a defense project, and the commercial applications of it began to be seen. And in sometime in around the early to mid 90s, the internet became commercialized and available to all of us, where we have this, what they used to call the access to the information superhighway. And so just to give you an understanding of sort of the fundamental features of how the internet is connected and how this network of networks is connected, the global internet is a network of networks with data files and website information stored on servers and data centers all across the globe. So all of this talk about cloud service or clouds and wireless devices sort of obscures the fundamental fact that the internet is physical infrastructure on Earth. Yes, there are aspects that travel through the air, so to speak, or through radio waves or light waves, but the actual ability to connect all of this and for these computers and devices and data centers to be connected to one another is all connected by physical infrastructure on Earth. And if you ever get a chance to go on YouTube, there's some fascinating videos about these undersea backbone cables that connect the global internet. So this slide here just gives you a visual representation of where these undersea cables kind of come into ports and are connected to various continents across the globe. Now, this particular slide shows the backbone or long haul network in the United States. And I always look at this internet backbone in the United States as being akin to our internet highway system. These are the routes and lines and by which all of the major traffic is transported. It's how computer information or data goes from California to all the way over to New York, or from California down to Florida. It is transported along these major access points in this backbone long haul network. Now, the closer you get to where we live and work, there's this connective tissue between the backbone long haul networks and the local networks that we all use. And that is called the middle mile network. But before we get there, this is sort of, we zero in on sort of the backbone network. And so for example, traffic might be routed, major internet traffic will be routed from, say, a data center in Chicago, go over to New York, down to Baltimore. And you see down there at the bottom of the slide that Tyson's Corner, Ashburn. Fun fact, Ashburn, which is in Northern Virginia, is known as the data center capital of the world. It is it's the first in the world data center to surpass a gigawatt of data center capacity. I think London is a distant second, but every major player in terms of the information that's online has servers there in Ashburn. We're talking Amazon, Google, Microsoft, Facebook, etc. 70% of all internet traffic is routed through Ashburn every day. Now, as you get closer, that connective tissue from the long haul backbone network that spans the country to these more regional networks are what they call middle mile networks, to refer to that middle section between the backbone and that last mile to the home. And middle mile networks are what are connecting the private facilities, big anchor institutions in communities, hospitals, public safety organizations. And one thing I should mention as well, the undersea cables in the global internet, the long haul backbone network across the country, and middle mile networks all across the country, it's all fiber. All fiber. Now, last mile connectivity is what we are all fundamentally concerned about. It's what BEAD focuses on in large part. There is some stuff in there about middle mile connectivity, because middle mile networks are actually very important to drastically lower the cost of deploying what they call last mile networks. And by last mile networks, that terminology refers to the technology that connects to individual homes and businesses within the communities that we live. And so I think of the middle mile networks as akin to state highways and major routes and roads, and last mile connectivity as being akin to the individual streets and driveways that get you from the highways to your front door of your home or to your business. And I should also note that last mile is a concept, not a literal term. It doesn't mean a literal last mile. It just means that last part of connectivity that brings the global internet, or what we all call the internet, to our individual homes and businesses. And when it comes to last mile connectivity, there are a handful of internet technologies that are used to make those connections. Wire technology, there's essentially three: DSL, cable, and fiber connectivity. Now, remember, it's fiber all the way back, from the global internet to the long haul backbone to middle mile networks. It's fiber all the way there. That last mile connectivity are these three sort of different choices, if you will. Now, DSL, as some of you may be familiar, and if you have DSL, you're probably going, oh my God, that can't be considered broadband. And you'd be raising a good point, because DSL is essentially antiquated copper wiring that's been around for decades, which is why it's degraded in so many places. And unless you live really close to one of the substations, you're probably not getting the kind of connectivity that will allow you to do things like send an email, and certainly not to have a Zoom call. So anyone who is hearing me clearly, and if your Zoom is working, I would step out on a limb to say that you probably do not have a DSL connection. In fact, DSL is being abandoned by most of the major carriers as we speak, because most DSL connections, digital subscriber line is what it stands for, they don't meet the minimum definition or the minimum speed to even be called broadband. In fact, some states, as they're putting together their BEAD plans, have specifically said, we're not even going to consider DSL broadband for our purposes of investing in new infrastructure. So if a place has DSL, we're going to consider that community or that kind of connectivity as being unserved with broadband. Now, cable, which is a hybrid, they use HFC, a hybrid fiber coaxial. It's sort of a combination where cable is how most people get their internet. And that's, without going too far into it, is because cable companies realized when they were delivering their, building their TV services, they realized that they could also deliver internet along those same cable lines. And so they ended up, and because it's so superior to DSL, and became the sort of the default, that became sort of the primary and best internet connective technology out there for a number of years, until the cost of fiber became such that it made sense and it was economically feasible to deploy fiber to the home, or last mile fiber connectivity. Now, cable wiring or cable connections, to the extent that they're, you've got reliable service, it's pretty good on the download side, pretty good. You can get up to a gig download side. On the upload side, not so much. Now, cable companies are starting to roll out DOCSIS 4.0, which they're saying is going to, give something close to symmetrical speeds and vastly improve upload. They're in the beginning stages of rolling that out. So that's pretty much the story with DSL and cable. But then there's the king of connectivity, which is fiber. So we're going to spend a few moments talking about fiber. Now, why do they call fiber future-proof? You hear that term thrown around a lot. And essentially, it's because it delivers faster, symmetrical, meaning the same download speeds and upload speeds. It's more durable, it's more reliable, and it has near limitless capacity and bandwidth to deliver internet connectivity. So with fiber, there isn't so much a problem of, even if you have this massive highway, well, what about when there's all this traffic and people are in a traffic jam? With fiber, because of the capacity it has, it really minimizes that problem of so many cars trying to share the road at the same time. And so BEAD, which is what many of us are focused on as states are preparing their plans and are preparing to get their BEAD allocations, BEAD prioritizes fiber networks, and for good reason, because they are future-proof in the sense that they're faster, they're more durable, they're more reliable, and they tend to live longer. Because once you build a fiber network, yes, there can be problems with fiber cuts, et cetera, but essentially the upgrades to the network are about switching out the electronics on the ends of the network, so that the capacity of fiber is really only determined by the electronics on the end of the network and not the physical medium itself. And so, much like when you're building roads and bridges, you're not thinking about, well, how do we build a good enough road for today? You're thinking about building infrastructure that's going to last for a generation or two. And so it makes sense to be building infrastructure that is going to be around for a good while, so that 10 years from now, we're not back right where we were saying, oh my goodness, the infrastructure is degraded, we need to do this all over again. Now, fiber, as many of you may, or maybe some of you don't know, the fiber optic itself, what is referred to that fiber optic strand that you see here pictured, those, if you look at that bottom right picture, there's that little tiny strands that stick out. That's what the fiber actually is. These hair thin strands made of this special glass that transmits our data, the ones and zeros, along light waves. And so when they say that fiber is a superior technology, that isn't just a tagline or a marketing ploy of the Fiber Broadband Association, it is physics. Fiber is a superior technology, and it's in terms of reliability, and the fact that the signal isn't as easily disrupted or degraded. These things are not in dispute. There's two ways to deploy fiber to the home or fiber to the premise, whatever sort of acronym you want to use. But that last mile fiber connectivity is deployed in essentially one of two ways: either aerial, what they call aerial fiber deployment, or underground, above ground, underground. And when you're talking about aerial fiber construction, you're talking about essentially attaching fiber to utility poles that are, throughout a community, where is how you're getting your power, how you're getting, if you still have a landline on your phone, those same utility poles are used to deploy aerial fiber networks. And I should say, if you look at that, well, these pictures here are to show you kind of fiber lines on the utility poles. That top right picture, that horseshoe looking thing, is where there's extra slack in the fiber. So when there is a problem, if new fiber needs to be spliced, you've got some sort of extra slack, and it's easier to fix. And then you've got some I guess you could call it like extra capacity fiber in that little black box looking thing that's hanging from the wire in that top right picture. Now, when you look at utility poles, sometimes they look like a mess to sort of the common eye, but they're actually there's quite specific standards as to what goes where on a utility pole. And so the utility pole, without trying to read all of the small print here, and these slides will be available. The basic thing to remember in terms of where things are placed is that power goes up on top, and the communication stuff sort of goes underneath that. And there are distances and codes about how far away each of those things needs to be ready, or needs to be from one another. The power lines, the transformers, etc. And then the communication lines that go, you see that bottom, see that communication line that goes along the bottom there. And there's a particular distance from the ground to where that needs to be. So all of these things are part of the engineering of aerial fiber deployments. But I think the primary thing that I want you to remember is not the pole specifications, but that one of the challenges in building fiber networks that communities will have to face, and if you're a community that is considering a proposal to build a fiber network, there are certain questions you're going to want to really dig into and understand. One of those is, who owns the utility pole? That is super important, because if the pole is owned by a telecom company, which many of them are, many poles are owned by, electric utilities, but many poles are owned by, telecommunication companies, they're not exactly in a rush to give space to a competitor on their pole. Now, by law, they're not allowed to deny access, but there are a lot of things that can happen to sort of do some foot dragging to extend out that process that can really wreak havoc on construction timelines and cost. In many rural communities, there are electric cooperatives. The wonderful thing about electric cooperatives, and we're going to talk a little bit more about them in a moment, is that they own the utility poles. And so that can be a tremendous benefit when it comes to deploying aerial fiber, particularly in rural communities. But the whole pole attachment process involves what they call make-ready work, which means there has to be a determination by the pole owner of, if the pole is ready to receive a fiber attachment, if there's any kind of work, if the pole needs to be replaced, if there's any kind of work that needs to be done in order to accommodate that fiber attachment. And depending on how that permitting and process works, it can delay and add significant construction costs to the point where we've seen projects that had initially been proposed as aerial construction, but because they hit such a roadblock on the pole attachment, they decided, you know what, it's easier and actually cheaper to do underground deployment, which typically is actually more expensive, which we'll talk about on the next slide. I should also note that the FCC hasn't ruled on pole attachment, so there isn't really a standard federal way of handling these things. And so in each state sort of has their own rules. Some states have tried to streamline the process to make it easier for these fiber deployments and access to utility poles, but it's very much a mishmash depending on which state you're in. But these questions are very important for communities that are considering deploying fiber aerially. Now, of course, the other way of doing it is underground, meaning you're burying the fiber lines. And for that, it means putting conduit in the ground, which are essentially the tubes that you're putting the fiber in. The tubes are of course, to protect the fiber. I mean, the fiber strands itself, they do have some cladding and coating around it, but even that will go inside of conduit for additional layers of protection. Now, as I mentioned before, typically it's more expensive to do underground fiber construction than aerial construction, but it really depends on that utility pole question, and as well as some other factors. Also, to bury fiber requires expensive machinery, directional boring machines, backhoes, all of these things to dig these trenches require expensive labor, expensive machines. Now, there's something that is a little less expensive and a little less cumbersome than, digging trenches, which is something that they call micro trenching, which is a fairly new way of deploying fiber underground. We're talking, as opposed to it being, several feet underground, we're talking about maybe several inches underground, and it's typically they'll cut a hole, as you can see in this picture, a strand in the road and lay the fiber in there. Now, again, this is a sort of new thing, and I've heard mixed results on these things that I think have a lot to do with weather conditions. In places that are particularly cold, microtrenching may not be such a great idea. Also, by the way, Department of Public Works don't really like it when you're ripping up their roads, especially because it reduces the lifespan of that road. So there's those considerations as it relates to micro trenching. Another challenge when it comes to underground deployment is you have to have a really good sense, a precise sense of where other underground utilities are, gas, water lines, etc. And so finding where those are, and then even when you deploy your fiber, carefully marking it, because you don't want somebody to come along with a backhoe and accidentally cut your fiber line, which actually happens. Now, of course, when you deploy fiber underground, it's less impacted by environmental factors, storms, etc. So sometimes when you have storms that are knocking out utility poles and power goes out, fiber that's underground often is unaffected by any of that. But of course, when you're digging and deploying fiber underground, as wonderful as that fiber connection may be, you don't want to hit a gas main. Now, I said earlier that fiber optic networks are called future-proof, and for good reason. They may be future-proof, but they're not foolproof. There are certainly things that can happen that can cause problems to fiber networks. Trees sometimes fall on fiber lines that require replacing those lines, splicing, etc. But more often, what causes a fiber connection disruption is caused by some kind of backhoe cut, as you can kind of see in that top right picture, where some other construction crew is working and they unintentionally dig and cut your fiber line. And that's typically what may lead to those kind of disruptions in fiber service. But then you look at the bottom two pictures, on one on the left-hand side and one in the middle. For some reason, chipmunks love to chow down on fiber lines. And so sometimes that's what that is. They're a chipmunk who sank their teeth into a fiber line, and they've been known to cause some disruptions. Now, the kind of Kevlar that fiber is now put in, there's all these different materials that they're now putting around fiber lines to try to make that a less frequent occurrence. It doesn't happen like all the time, but it's something to think about. And then, of course, sometimes there's birds on the line. I'm going to give people the benefit of the doubt because, as you can see in that middle picture, that's a bullet in the fiber line. And as you can imagine, that can cause a disruption as well. Now, let's talk briefly about the economics of fiber deployment. The thing to know about fiber deployments is, of all of the connective technologies, fiber has the highest capital expenditures. They have the highest upfront cost. And so here, we looked at I guess these are broad sort of back of the envelope kind of calculations. And so the cost to build out fiber in a Midwestern city here, looking at directional boring and breaking down the cost per foot. So you see conduit is not very expensive, $1 per foot. Fiber itself, the cost of fiber is not very expensive, $1 to $2 per foot. Permitting isn't all that expensive. All of the other equipment that you're going to need, the handholds, the couplers, the splicing equipment, the locate wires, all of that is not very expensive. The bulk of the cost in deploying fiber is labor, as you can see here. Now, though fiber networks have higher upfront cost, they have lower operating costs than other forms of technology, and they last longer. So that is something that a lot of communities take into consideration. Certainly Congress and the federal government in their prioritizing fiber networks have taken place, because in that calculation, they're saying, okay, higher upfront cost, but longer lifespan, cheaper maintenance. When you have problems with fiber connections, you're not very often rolling trucks and crews and equipment out to fix every little problem. We at our team, we've gone around the country to visit various, fiber network operators, and we hear them say all the time that probably about 90 to 95% of their service calls can be handled from a desk in their operations center. And they usually have to do with the router in the home or some other problem, but it's not very much the case where they have to roll out a truck to fix something in the actual physical infrastructure. Now, I wanted to, before we talk a little bit about wireless technology, I wanted to say a little something about the Affordable Connectivity Program, which is also part of the infrastructure law, which is the program that provides a $30 a month discount to low-income eligible households. Congress funded it at $14.2 billion. There's a burn rate where we've got right now about 40% of eligible households are enrolled and are receiving the benefit. And at that rate, we're going through that money at about $600 million a month. And some time ago, we created this dashboard, which you see pictured here on the slide, largely because we not only wanted to see what enrollment rates look like in every zip code across the country, and this is an interactive dashboard, but we were primarily driven by the question, how long will it take for this money to run out? It turns out that money is going to run out in the spring, early summer of 2024. And there is not yet on the horizon a long-term funding solution. The White House has recently requested another $6 billion to get the program to the end of 2024. But we really need a long-term solution for two reasons. One, affordability is a tremendous barrier. Even when the physical infrastructure is in place, the number one reason cited in survey after survey after survey of why people don't have home internet access is affordability. And so having this kind of subsidy or benefit for households to get online is very important. But there's another very important reason that this program we need to find a long-term funding solution, is because of the economics as it relates to building out to rural areas. I should go back real quick to that last slide. If you look down at the bottom in terms of fiber networks, you see that the cost of connecting a home is about $1,000 when you're talking about an urban household. It's less, of course, when you're talking about a multi-dwelling unit like an apartment building or a condominium complex, just because um, you're essentially running fiber to the building and then splitting things, throughout the neighborhood. But in rural areas, and this is one of the reasons why physical infrastructure is so lacking, is that it's much more expensive to build out infrastructure to areas where that are sparsely populated, where homes and buildings are far apart from one another compared to densely populated neighborhoods. And so this is a rough estimate. You're looking at $3,000 to $5,000 per connection per rural household or location. So when we talk about the Affordable Connectivity Program, not only is it an important benefit for individual households, but when you're an internet service provider and you're looking to make a business case, or you're considering building out a network in a rural community that's sparsely populated, and you also know that a sizable chunk of your potential subscriber base can't really afford the service without some form of subsidy, you need to know that this program is in place. Otherwise, you may be discouraged and say, you know what, it's really not worth it, because it's going to be we won't be able to sustain that network if we don't have that kind of stable revenue coming in, particularly if a large number of people are going to be relying on the Affordable Connectivity Program to even be able to afford the service. Now, wireless technology, of course, is another very cool technology that is being used to make these last mile connections. And like I said, wireless is cool. I think it's pretty cool because who really likes wires all over the place? So that in and of itself is super attractive. Out of sight, out of mind. Like beam this stuff to my device. It's much better. Now, there's kind of two different main categories of wireless technology. There's the wireless networks that our mobile devices use, which is great when we're out and about. This picture here is of a cell tower, and so you've got your cell phone. My cell phone will go to my router. My router is going to the utility pole in my neighborhood, which is then sending it to a signal to a wireless tower. But even in this wireless tower, there is a fiber that's connected behind this wireless tower. So again, fiber is super important to the workings of the entire network, but even when it comes to wireless technology. So all of this talk that we hear about 4G and 5G and LTE and all that mobile technology is wonderful, especially when we're mobile. But it's not adequate to meet our, all of our needs, particularly when you're talking about things like work from home, online learning, telehealth. There are certain online applications that require more bandwidth and better connectivity than mobile wireless technology affords, or provides, I should say. But there are also fixed wireless networks that are high capacity that can meet household needs, depending on the terrain. Fixed wireless networks work much better in flat areas. That's where you get the best coverage. And fixed wireless networks will sometimes struggle in more mountainous regions, like places like Appalachia. And that has a lot to do with the line of sight. So you may hear people say, it's super hard to drill in mountains and to deploy fiber. But it turns out it's also actually pretty hard to deliver a wireless signal in mountain regions. So if we look at this next slide here, this gives a rudimentary sort of picture of how a fixed wireless network sort of operates. And so you've got the global internet there off to your right. And then you've got that fiber connection to the wireless tower. And then that wireless tower is beaming out and receiving through radio signals the two-way information. Then on individual homes and businesses affixed to the roof, there's the antenna. And then there's the wiring from the antenna to your router in your home. And then within your home, now you're talking about Wi-Fi within the home, delivering that signal to your devices within the home. There's also a really an emerging sort of wireless technology that is called CBRS, Citizens Band Radio Service, and this uses the radio spectrum that's managed by the federal government. It's mostly used by the military, and it can do some really cool things, but it's limited. And we've seen that in urban areas, for example, it really hasn't got to the point yet where it can deliver high quality speeds. But it works great where no one else is using the spectrum. And so there's sort of an order of ranking as to who gets to, dibs on the spectrum. Of course, the first priority going to the military, the Navy primarily. And even though the Navy doesn't just operate ships, of course, that spectrum is much more in need of use on the coast than it is in, say, Kentucky or Kansas, where, there's not a lot of battleships. Not to say that the Navy doesn't have use for it there, but still, if we can figure out a better way to manage the spectrum, we think that CBRS holds a lot of promise. But here's the thing. You're probably in your communities are going to be sold and hear from vendors who are going to say CBRS is great. You should it's cheaper to deploy. It works terrific. It's going to solve all your needs. I will say that there's mixed results, and it very much depends on your area, the terrain, the use of spectrum, et cetera. And so if you're considering CBRS, even as a gap network, meaning to fill in gaps, to certain locations that may not have internet access, it's very important that you work with a professional consulting firm on this. Now, just to bring it home here, when we're talking about this last mile connectivity, we're really talking about the unserved and underserved regions within Appalachia. And so these, if any of you were here when I did several weeks ago, the funding slide, this just kind of lets you know what areas are going to be targeted by BEAD. And so that's what this slide here is. And as I pointed out before, in West Virginia, 100% of the unserved locations, which is what BEAD prioritizes, are in Appalachia. So that's great news. So these last mile technologies are going to be used to bridge the digital divide in this region. And what most states want and what BEAD prioritizes is fiber networks. However, if you look at some of the state BEAD plans, all of them or most of them recognize that it may not be economically feasible to deploy fiber everywhere. So it may be mostly fiber, but certain hard to reach locations where the terrain works, it may be some kind of fixed wireless solution. And then here is just a slide to remind everyone here of how much each state is getting in terms of their BEAD allocation that will target unserved and underserved regions. But the thing here to remember, and I hope that you really take away, is regardless of the technology that a particular community may zero in on, be it wireless or some form of wire technology, it's important to remember that ultimately this really isn't about technology. It's about power. It's about poverty. And for the past 30 years, we've essentially relied on monopoly providers for internet connectivity. And here we are, after billions of dollars in subsidies to these companies, we still have this massive digital divide. And so I love this quote from our partners at Connect Humanity, who make an astute observation in that half of humanity right now is connected to high quality internet service. The other half will likely need to be connected by business models that are different than what we've done in the past. And so real quickly, I want to give you a quick overview of what those are. We call them community broadband networks. And at our program, this is something that we specialize in and that we track across the country and have been for the past 15 plus years. And they come in various forms and varieties. There's full-on municipal broadband networks where a municipality treats the internet infrastructure as a utility. And just like they build water systems or roads or schools, a municipality says, you know what, we're going to build our own local network. And many communities have done so. Most of those communities had an existing electric utility in those communities, but some communities didn't, and they created a broadband utility from scratch, essentially. And you also have electric cooperatives, and that I would point out, particularly in a lot of the states that are in the Appalachia region, electric cooperatives have really been at the forefront of bringing fiber to rural communities, in part because many of the electric cooperatives built fiber networks for their what they call their SCADA systems to monitor their electric grid and their electric services and detect outages before they happen, et cetera, et cetera. And they realize that if we just overbuild our SCADA fiber networks a little bit, we can actually extend this service and deliver fiber to the home and fiber to businesses, which is what a lot of these member-owned organizations overwhelmingly voted. They said, yes, please do that. And so in many states that have electric cooperatives, they are really at the forefront of driving fiber out to rural communities. In fact, in the state of Virginia, that's really at the heart of their plan to bring fiber to rural communities in Virginia, which is to really lean on electric utilities and electric cooperatives. One thing that's not pictured here that also is a model is what they call P3 networks, or public-private partnerships, where a community or a municipality will partner with a small ISP to build out a community-wide network. And there's various ways in which that can be structured. The best way is where the community ultimately owns the infrastructure and the assets, so that they're not in a position where that ISP gets bought by some private equity firm, and 5 years from now, you're wondering why the price of internet service is so high. Now, in the state of Vermont, a very rural state, I mean, in fact, almost the entire state is rural. What they're doing there is they have established what they call communication union districts. And the enabling legislation allowed essentially 2 or more towns to come together to form a telecommunications utility, which allows for them to raise money, to apply for grants, to even issue debt. They can't do it through taxes, but this is the primary vehicle by which Vermont is bringing fiber to the home all across the state. This is a map that shows the dozen or so communication union districts that have been formed and that have been working like gangbusters and delivering fiber connectivity all across that state. This is a map of the electric cooperatives who have deployed fiber. I always like to point out, if you can see my cursor, I always like to point out North Dakota, because people like to say, oh, fiber is so difficult to deploy in certain terrains. But you see here, North Dakota is almost completely covered by fiber, largely because of the electric cooperatives in that state. And I think that if a state as inhospitable to fiber deployment as North Dakota is, if they can manage to somehow cover their entire state in fiber, chances are your state can do it as well. And then this is a map here you see on the right of some various community broadband networks, mostly municipal networks and electric cooperatives across the country, who have built their own infrastructure and have done so with great success. And they've done it because in almost every instance, the service is faster, it's more reliable, and it's affordable. And it's because of the difference in incentives. They're thinking about this in terms of decades, generations, not how do we get a return on investment in the first couple of years of operation. And so it's a whole different incentive structure. And every year, PC Magazine ranks the fastest ISPs in the nation. Those on the left are either small ISPs. Many of those have partnered with communities in public-private partnerships, or their municipal networks like Chattanooga's there, EPB in the middle there, you see how well they do and how they outperform the big guys, mostly because those are fiber networks, but also because their business models are very much different. These are just some clips here, and I need to wrap up on what is considered the golden child of municipal broadband networks. I think the most celebrated one, which is in Chattanooga, built out of they invested about 220 million to build out a citywide fiber network, and an independent study that's referred to in that top left-hand corner found that that community has reaped a $2.7 billion return on investment in its first 10 years of operation. And also because they have such a great network and were able to set up a program to deliver free fiber service to all low-income families during the pandemic and for a decade, they're not as concerned about what happens with ACP as other communities are and should. So again, this challenge that's before us is not about the technology. The same fiber networks, the same technology that small ISPs, that electric cooperatives are using to connect people, it's the same technology that's being used by the Comcast, the AT&T, the Charter Spectrums, the Verizons of the world. Internet infrastructure is more about power, political will, and community engagement. So I thank you for coming with me on this trip, and I'm going to turn it back over to Sarah.